Let's start. Today we have Shivang Jindal from the University of Edinburgh, and he will speak about cohomological whole algebra of cyclic quivers and an integrable form of affine Yangian. Hopefully he will explain these words. Okay, please, Jim.
Thank you, and for giving me opportunity to give a talk in this seminar. As you may hear, my throat is slightly hoarse, so I've written a lot of text. So if I'm not clear, I would advise you to look at the text. So I'm going to start with explaining what are these topics. What does CoHA mean? What does an integral form means? What does a Yangian mean? So here's the plan. So first I will say a few words about Yangians and the motivation that we want to have a geometric construction of Yangians. Then I will explain what homological whole algebra means, and then after stating the main result, I will explain how these theorems are proved by using techniques from DT theory. So I'll start. So what are Yangians? So Yangians are certain quantum groups certain algebras which appear when someone tries to find solutions of rational solutions to Yang-Baxter equations. So what does this mean? So if you take any semi-simple Lie algebra and you can adjoint a variable u and the Lie algebra of like polynomial Lie algebra with coefficients in G. So this is a Lie algebra which is defined by the Lie bracket, where you have a general element of the Lie algebra G with some power of u, and another element of G with power of u, and then the commutator is just the Lie algebra in G and times u with power of u. Now, so this is the Lie algebra G bracket u. And the Yangians are defined by Drinfeld in 80s. These are certain algebras which are defined over some formal parameter h, which are non-commutative and also non-co-commutative, and they deform the universal enveloping algebra of this Lie algebra. So what do I mean by deform? So the deformation here means that there exists some filtration on the Yangian, so on this algebra y h of G, such that if you take the associated grid algebra with respect to this filtration, then what you get is the universal enveloping algebra of this Lie algebra G bracket U. So, or equivalently, in this case, like in the classical cases where it's defined, you can just set h equals to 0, and what you get is the universal enveloping algebra of G of U. And for h not equal to 0, you get some algebras which are not isomorphic, which are all isomorphic. So it's deformation in that sense. So now there is a geometric construction of Yangian due to Kunko. So I will not say how the construction goes, but the general story is that you start with any quiver. A quiver is just a directed graph. So you can just imagine some directed graph. Then Malik and Okunko, they constructed this something called R matrices. So these R matrices are the solutions of Yang-Baxter equation, but they constructed geometrically by using the cohomology of Nakajima quiver varieties. So given any quiver, you can associate some varieties called Nakajima varieties, and these are symplectic varieties. So there's an action of torus which scales the symplectic form, and by considering the equivalent cohomology of this Nakajima variety, the molecular construct certain algebras which are denoted by YMOQ. So these are certain algebras which behave very much like Yangians, in the sense that there exists some filtration. So they in the paper they prove that it's not trivial. So there exists some filtration such that if you take the associated grid algebra with respect to that filtration, then what you get is universal enveloping algebra of some Lie algebra with the Lie algebra polynomials in this Lie algebra. So you take the Swiss grid, and then you get universal Hamilton module of GMOQ with bracket U. Now, this is very much reminiscent of how I defined Yangians before.
But this Lie algebra, it has nothing to do with the Lie algebra associated with the quiver.
So it is, so for the case of ADE quivers, it is true that this Lie algebra is same as the Kac-Moody Lie algebra you can associate with the quiver. In general, it's recently proved that for a given quiver Q, you can associate you have the Kac polynomial, and then you can build up a Kac-Moody Lie algebra where the generators are defined by the intersection cohomology of the coarse moduli spaces, and it turned out to be same as that. But for classical cases, for example, for AD cases, it's the same Lie algebra. In fact, that's what I'm going to say next. So for Jordan quiver, Malik and Okunkov proved in their paper that in fact this algebra which they define is exactly the affine Yangian of GL1. And for AD quivers, Michael McBreen in their thesis proved that the Mollico-Kunkov Yangian is exactly the Drinfeld Yangian, which I explained in the slide before. In particular, the Mollico-Kunkov Lie algebra, GMO2, is same as the Kac-Moody Lie algebra, so to Q. Now, there's another parallel construction which goes via Hall algebra, and which is what I'm going to explain, which is the purpose of this talk. So I will start by explaining what are quivers, and then we go through it. So what is a quiver? So quiver is just a directed graph with some set of vertices and edges. So for example, a Jordan quiver is just a graph with one vertex and a loop. Similarly, the object we are interested in, the cyclic quiver. So cyclic quiver is just some. So for example, here I explain the cyclic quiver of length 3. So I say Q. I mean, it's kind of confusing notation, but it will be clear why I say Q2. But it's a quiver it's a graph with 3 vertices and 3 arrows in between that it forms a cycle. Similarly, by QK, I will denote a quiver with a plus 1 vertices, and then I have a cycle. Basically, you allow any quiver. Now we consider its path algebra. So path algebra is just an algebra where on a vector space, where this vector space is defined by the paths in the graph. So for the case of Jordan quiver, we have one loop, and we can take as many paths as we want. We can go on the loop once, or we can go twice, and then we can keep going up. And the product in the path algebra is defined by concatenation of the paths. So based on what I just said, for example, the path algebra of Jordan quiver is just the polynomial ring in the Now given, so now we start with quiver, which is a combinatorial data, we now have an algebra. What we're interested is in the representations of the path algebra. So the representation of path algebra is just basically a data where for every vertex we associate a vector space, and for every arrow we associate a homomorphism, a linear map. So the dimensions of this vector space is called the dimension vector. So we look at the d-dimensional representations of path algebra, and there is a geometric quotient stack which parameterizes such representations. So we consider MDQ as so this MDQ is a quotient stack where we consider the representations. So we just associate some linear maps, and so for every arrow you associate some linear map, and then you look at it up to isomorphism. So there's always a change of basis kind of action going on. So you can always take the quotient by the gauge group, and this stack parameterizes representations of the path algebra. So for instance, if we take the case of Jordan quiver, then we basically have just have one vertex. We just have one vertex and a loop. So we can So on every vertex, we can associate an endomorphism. So because there's only one vertex, and then we look at it up to this group action given by conjugation. So, yeah. So now we have we know what is the moduli of representation of quiver. We go to the next step. We consider the preprojective algebra. So now we have the quiver. We consider a double quiver. So we add an arrow in the opposite direction, and we define preprojective algebra to be the quotient of this double path algebra of the double quiver with these relations. So which are just some sort of commutation relation between the arrows. So this might not make, but let me explain the why this is kind of natural. So what we can do is that we can take the cotangent bundle of the representations. So in previous slide, I explained what are the representation of the path algebra, and I take the cotangent bundle. So cotangent bundle of an affine space would just mean adding an arrow in the opposite direction. So that's why we add the arrow in the opposite direction, and we get this rep t of CQ Q bar. And so this is a cotangent bundle. In particular, it's symplectic, so you always have a moment map. And the moduli of representation of preprojective algebra are exactly the moment map. So we have the moment map, and we can take the inverse at 0. So and then we again take the quotient by the gauge law. So this is the preprojective algebra in its moduli space. So let me give some examples. So now in the case of Jordan quiver, we had one loop. Now we can when we take the double algebra, we add another loop, and we impose the relation that these two loops commute to each other. So what we get is that preprojective algebra Jordan quiver is just the polynomial ring in two variables. While if you look at the d-dimensional representations of the preprojective algebra, then this just means you have two commuting matrices. You're looking at it up to isomorphism. And grammatically, this just means you are looking at torsion sheaves on A2, because a torsion sheaf on A2 would just mean that you have a vector space with an action of this x and y. A finite dimensional vector space with action of x and y which commute with each other, which is equivalently commuting variety. And so this is why modular representations of preprojective algebra is exactly torsion sheaves on A2. The case which we are interested in is the case of cyclic quiver, where these are not exactly like the same, but they are close enough. In a sense, if we take the finite subgroup of SL2, cyclic subgroup of SL2, where it is embedded by taking the +1 through primitive root of unity on the diagonal. And so we have the primitive root of unity and the inverse on the diagonal. And this group acts on C2 by just taking, you have x and y tends to omega x and omega inverse y, where omega is the primitive root of unity. Now, if we take the quotient, then it has singularity at the origin, and it is known that it has it has a unique minimal resolution, which is called the Kleinian surface. So we take this surface as K. Then then there's a derived equivalence between the coherent sheaves over this surface and the representations of preprojective algebra of the cyclic quiver. So in some sense, preprojective algebra is like non-commutative model of these kind of varieties, so two Calabi varieties. And this is why people study that. So now let T be any torus which acts on this stack. So now we can construct this cohomological algebra of preprojective algebra. So what is this? So it's a general technique which I think is like has been spoken many times in the seminar. So how do I? So we take the set of we take the stack of short exact sequences. So let x d comma e. So with two different dimensions d and e, we take the stack of short exact sequences. So it is a stack which parameterizes the representation of preprojective algebra, with a short exact sequence of representation of preprojective algebra. So we have short exact sequence, where the first object in the short exact sequence is of dimension d, and the third object is of dimension e, and so consequently the middle term is of dimension d plus e. And now, given the stack, we have two different maps. So we have a map which remembers the first and third term, which is this map, or we can just remember the second term. So if we remember the first and third term, we can define a map to the moduli of d-dimensional representations times moduli of e-dimensional representations. Or if we remember only the second term, then again we get a map to d plus e-dimensional representations. Now, the point is that this map is proper simply because if you look at the fibers of this map, then we are looking at some kind of quotients, which is basically code scheme. So we can ensure that this map is proper. This map is not proper. It is not proper. It's not even smooth because this stack, all three stacks are not smooth. But it can be shown that this map is of special type. It's a locally closed immersion. In particular, if you take the Fourier-Moore homology, then you can take pullback along this map called the virtual pullback, and you can take forward along this map. So if you take the Fourier-Moore homology, which I remind is just the dual of compactly supported homology, then one can take the Fourier-Moore homology of these spaces and get an element. So one can start with Fourier-Moore homology of this. Then you take the pullback, you get to the Fourier-Moore homology of the term in the middle, and then finally you go to the looking forward, we get to the Fourier-Moore homology of moduli of d plus e dimensions, and taking direct sum over all d and e and applying Kuhn's isomorphism, Schiffmann and Vasserot Jordan quiver, and Yang for any general quiver, prove that there is a associative algebra on this space where we take the direct sum over all dimension vectors. We take the Fourier-Moore homology of d-dimensional representation of preprojective algebra, and so now we just take the usual Fourier-Moore homology, but here I wrote ver because I want this algebra to be cohomologically graded, in the sense that if you have two elements of different cohomological degree, then I want this product to send it to cohomological degree, which is given by adding these two cohomological degree. So we do a slight twist. We just manually put this shift, and then this becomes a graded associative algebra. And here it means that because we have that torus on this stack, we can also take the equivalent cohomology. So we also get similar structure on the T equivalent cohomology. Now, this algebra is defined also in some sense very abstract way, and it's not very easy to calculate, but there are some calculations known. So for the case of ADE quiver, it is known due to result of Yang, and Schiffmann and Vasserot in 2017 that in fact for the case of ADE quiver, this algebra for some case of torus is exactly the positive half of the Drinfeld Yangian. Similarly, for the case of Jordan quiver, it was shown by like combined work of Davison and Rapek and Yang in 2020 and Schiffmann Vasserot in 2012 that there is an isomorphism of algebras where you take preprojective CoHA for Jordan quiver and you get the positive half of a fine Yangian of GL1. Now, these two examples are also known for the case of Maulico-Kongo-Yangian, and this is exactly the positive half of Maulico-Kongo-Yangian, as I said before. And in fact, it's more generally true. There's a recent theorem of Marco Bota and Ben Davison and Oliver Schiffmann and Eric Vasserot 2023, where they show that for any quiver Q, in fact, there's an isomorphism of algebras where you have the cohomological algebra, preprojective algebra for some choice of torus. On the other hand, you have the Yangian, positive half of Yangian for any quiver. Now here, the choice of torus is in a way that it should be like the Yangian as defined requires you to have an action of torus which gives the symplectic form. So here we have to choose a torus which gives the symplectic form, but otherwise this is always true. So this is the things which are known, but other than these two examples, they're not other examples I'm aware of where these algebras are completely known. And in my work, I calculate them for cyclic Q. So
here I have a quick question. In
yeah.
the examples on the top, the GQ in this case, if Q, that's the finite dimensional simple Lie algebra. You take Yangian.
Yeah.
But in the bottom here, for the Jordan quiver, this is the affine GL1.
Yeah.
So how the two parameter H1, H2 get involved?
Like in the sense, I mean, I think it's more like, so, I mean, it's more like when you set H1 equal to 0, what you get is W1 plus infinity algebra. So, maybe
you have the C star T, the torus C star action. So I can see that will give one parameter in a certain sense. So here you have H1 and H2.
So here, I mean, we have we start with a dot with two loops, and we can scale both loops with different weights. So you get two parameter deformation.
I see. So if that goes back to the Yang and Joss in the previous page, that when you take the equivalent Brammer homology, and we would be taking the C star square.
Yeah, exactly. Yeah.
And how is the T here in this term is acting on this preprojective algebra? Will be acting on one component or diagonally?
Which theorem are you talking about? The theorem which is on the slide right now, or?
Yes, in this theorem here, because you have T is the one-dimensional torus.
So here, this is true for any torus. In fact, in particular, you can just not have torus also. So this is for any torus action, you can define algebra like that.
Okay, I see.
Yeah.
Okay.
Yeah, sorry for this confusion. I should have changed the notation. So, but this is for any torus. So usually, I mean, I think the original definition of Schiffmann and Vasserot, it was in the context of AGT conjecture, where they had this torus extra torus action to get the affine Yangian of GL1 at. But then later, people also worked with non-equivalent thing. So I just said this because this is when you have the torus action, it gives you deformation of the non-equivalent cohomological algebra.
Yes. Okay. Thank you.
So yeah, that is not much is known for the cases except Jordan quiver or the AD quiver, and my work calculate it for cyclic quiver. So for cyclic quiver, what we get is is a group which is originally defined by Nicolas Gouet in 2017. They define a affine Yangian of GLK. So this algebra is a defined. They deform certain central extension of universal enveloping algebra of this affine. So this by SLK hat I mean some central extension. So SLK with bracket. So it's a two-parameter deformation where you have basically the affine Lie algebra with one more bracket. So it's in some sense Yangian of. So it's like a definition of Yangian for affine Lie algebras. So now, as defined by Gouet, this algebra has a triangular decomposition, and the positive half of this algebra is an algebra over two parameters C, H1, H2, which generated by some and with some generators x plus IR in their notation with some relations. So these relations are much clear, and I will show you one slide where we see these relations. But there are some. So basically, point is that they define this algebra, which deforms the central extension of this. So we deform this universal enveloping algebra, and they have certain generators and relation definition. Now, on the other hand, we take the two torus as we just discussed. So we act on the so here I think I should have written. So here the first torus acts on so you have the arrows in the opposite direction, right? So on the original arrow you act by weight 1, 0, and on the other you act by 0, 1. In particular, if you can think that you are scaling one arrow with weight h1 and the opposite arrow with weight h2, then one can check that there is an algebra morphism from this positive half of this Yangian to this to this cohomological algebra which are defined, which is defined by sending these generators to certain particular elements of the CoHA, which are in dimensions which are in the smallest possible dimensions. So we take these elements alpha IR, which are certain elements inside the I dimensional representations of preprojective algebra. So I delta I is a tuple where you have is a dimension vector where you have 0 everywhere except on the ith entry. And so in particular when we look at this moduli space for this dimension vector, then there is no extra relation. So it's smooth. And in fact, the homology is exactly homology of equivalent homology of a point with bracket some variable u. And this alpha IR is exactly the UR. Is identified to UR in this ring. Now one can define this as an algebra-morphism. However, this is not a surjection. And that's exactly the point. I think this is one of the most crucial point, because this is usually in the other calculations, it's always
I'm a bit
ton
of
of
a,
surjection.
sorry to interrupt. I'm a bit of a confused. The M delta I, that's the stack, right?
Yeah.
You say isomorphic to it's that the equivalent cohomology or cohomology at the point with
Yeah.
one parameter. So what?
So if I take this stack, so if I look at this,
are you taking the
sorry.
homology of that stack?
Yeah, I meant homology of this. Sorry. Yeah.
It's a okay. So still it's T equivalent cohomology of that stack.
Yeah. Sorry, that's a very, very wrong thing which I wrote. Yeah, it's a
because in this case the stack, well, the right is a
Sorry.
single point, but you don't have a large group acting on it.
Sorry.
Okay, I see.
So you take the T equivalent T. So this is wrong. So you take the T equivalent homology of this stack. And I mean, yeah, like I agree that the torus action would be just trivial. So that's why you get the T equivalent homology of a point at the variable u.
And there is also GL1 equivalent cohomology, right? That's where the U is coming out.
Yeah.
Okay, thank you.
Because it's dimension vector 1, at least in the equation you have C star. Yeah.
That's right. Thank you.
Yeah. So this morphism has one can define this morphism. It's hard to check, like it requires some work to check that it's an algebra-morphism, but one can define this morphism. And the point is, in case of cyclic quiver, this is not a surjection. In particular, if we can take the fundamental class of the surface, it's something which will live in cohomological degree -2, while this map that defined the only living in cohomological degree which are positive. So in the image, so in this all these alpha Ri, these are of positive cohomological degrees, and this cohomological algebra is cohomologically graded. So whatever the image would be, would only have the positive cohomology degree. While in reality, there are terms of negative cohomological degree also on this. So this map doesn't become never be an isomorphism. In fact, it's an injection also, which I proved, but not a surjection. So we need to add some elements here to make it right. And so we define integral form of the Yangian defined by Goel. So we consider an algebra over 2 parameters with again some generators, and so I add some extra generator kr for every r greater than or equal to 0. Then the relations, so these are the usual affine Yangian relations, and I just add the element kr so that after multiplying by 13 elements, you have this is an element inside the original algebra. So I'm calling this an integral form because when you localize, in the sense that when you allow H1 H2 to be so like you take the tensor with the algebra. In particular, you allow H1 inverse or H2 inverse. Then this relation makes it doesn't say anything new because then this element Kr is already inside the algebra. While if I take the C H1 H2 algebra, then a priori this element is not inside the algebra. And so what you get is an integral form. And the main theorem is that after adding this element, there is an isomorphism of algebras. So you have the same, the map is defined by sending this xir to again alpha ir, which I defined before, while these elements kr are defined to certain generators, which I will explain later. But this is
again this integral, whatever CoHA, it cannot read the notation. It this algebra which you defined. This is the algebra on this slide, which you call y integral. On the next one, is it? It's a question about the notation formula. Integral form. Why do you call it? Why you have CoHA in the superscript, whatever?
it just because
yeah.
maybe I
Just
should
Yangian, some version of Yangian. There are many of them. So it has nothing to do with CoHA. That's what I mean.
I mean, it is isomorphic. So this is not something which appear. I mean, so like I have to define this like in a sense that without this AR added, this is this is the original definition of Yangian. And I have to.
I mean, it's not a geometric definition. CoHA, it's some algebra built on the cohomology of some stacks, whatever, blah, blah, blah.
Yeah.
And this is just an algebra defined by generators and relations.
Yeah.
Okay.
Yeah, I just call this integral CoHA because this is isomorphic to the CoHA.
Yeah, but after you proved it, but not before.
Okay.
Okay.
Sorry. Yeah. Sorry for yeah.
Can you go
So
back? Can you go back to the definition of this gamma delta R?
yeah, I will explain that.
Okay. So
Yeah. I mean, but moduli is just like this fundamental class of the surface and the tautological operators with it. But I will maybe try to explain it now. So
okay, thank you.
So basically, like I define this map and it's isomorphism, and the first thing is to even check that this is an morphism of algebras. Even the morphism of this map which I defined before, even to check that this is a morphism of algebras, requires some new techniques or some techniques like a priori, because of the way the product is defined on cohomological algebra. It's not like one cannot directly just check generators and relations. So what one do is to go through to add a loop on every vertex and do some kind of 3 Calabi completion. So what I'm gonna say is that this preprojective CoHA is difficult to work with because the stack is not smooth. But we can do something more by doing 3D with this story. So what does it mean? So the stack of the dimension of preprojective algebra parameter completion 2 Calabi category, while we can do a 3 Calabi completion by going to representation of Jacobi algebra. And what we do is we just add an endomorphism. So we just look at the representations of preprojective algebra with an endomorphism. And what we get is some kind of Jacobi algebra. And the representation of Jacobi algebra, the stack of representation of Jacobi algebra can be written.
Okay, can you return your slide so we will see? Can you share the screen again? Because we see you but don't see you. At least I do not see your slides.
For me, I can like slide is already.
I still see the
share it
slide.
again. I share it
I
out
can
again.
see. Mhm.
Try to share it again.
Yeah.
Okay, good. Great.
Yeah. Okay, so the moduli of representations of Jacobi algebra is a probability.
Sorry, no, it's again disappeared. It's for me.
Oh. Is it for everyone or?
I see it. I see the slide still.
You
can
see
see
the
it as well.
slide, so it's a bit strange.
We can wait a minute.
Am I alone? Because I have been seeing them before, like a minute ago, but now I clearly see the speaker, but I do not see slides. Am I alone? If other people see slides, then that's okay. I can follow.
Yeah, I think we can see it.
We can see the slides.
Okay, good. Okay, then just go ahead.
I mean, I can try again just for a yeah. Maybe I will try again. Just stop share and it works.
Yeah, don't worry. I will follow. Yeah, and now I see them. Very strange. I don't know. Maybe it's a Zoom version which I'm using. Yeah. Okay.
Yeah, perfect. Yeah. Okay, so we go to study of Jacobi algebra. So let me define what I mean by Jacobi algebra. So we started with any keyword. Now we look at we take something called potential. So potential is just a linear combination of cyclic elements in the path algebra. Now, given a potential, for every arrow in the quiver, one can define a non-commutative derivative. So what we do is for any cycle W, we can take this sum. So you look at the arrows which are in this cycle, and then for every arrow which looks like every cycle which looks like CAB for this arrow A, you just take sum over BC, and this defines a non-commutative derivative, and then you linearly extend it to linear combination of the cyclic elements. So I mean, a priori the potential can be a linear combination of cyclic elements, when this derivative is defined only for cyclic elements. Then the Jacobi algebra is defined as the quotient of the path algebra with the relations coming from these non-commutative derivatives. So let me give an example to explain what's going on. So for any symmetric quiver, there is a general recipe. So what we start, we start with a quiver. We add a loop in the opposite, add an arrow in the opposite direction, and then for every vertex we add a loop. And then so we start with the quiver. You do doubling, so you add the arrow in the opposite direction, and then you add loops on every vertex. So let's call these loops omega I, and the double arrow, the arrow in the opposite direction A star. Then this potential is just defined in this way. And so, for example, let's consider Jordan quiver. So we have a dot with a loop. Now we add another arrow in the opposite direction, which just means another loop. And then we add another loop. So we have a dot with 3 loops. And the potential is exactly, so if you have 3 loops, x, y, z, then the potential is just x, y, z minus x, z, y. And when we take these non-commutative derivatives, then these are exactly the relations which impose the condition that these these loops x, y, z, they commute to each other. So Jacobi algebra for the triple Jordan quiver with this potential is just polynomial ring in 3 variables. And in general, for any quiver, if we do this construction and consider Jacobi algebra, then it's exactly the preprojective algebra attached with a variable omega. So in particular, if you look at the representations of Jacobi algebra of triple quiver with triple potential, then that's exactly representation of preprojective algebra with an endomorphism. Okay, so let me give another example. So for example, triple cyclic quiver, you have, this is a cyclic quiver of length 4. So you have 4 vertex. The original arrows are A01, A0, A12, A23, 0. Then you add arrow in the opposite direction. And then for every vertex, you add loops. And then define a potential given in this specific way. And my favorite example of this is conifold. So you start with a quiver with 2 vertex and 2 arrows in one direction, 2 arrows in the opposite direction. And then it's given a potential given by going this way, but coming back by row C, then going back by row B, then going by D. Or you come back by D, then you come by C. Again, this potential is ACBD minus ADBC. Then there is a derived equivalence between the representations of Jacobi algebra associated to this quiver with potential and the current sheaves over the resolved conifold. By resolved conifold, I mean the total space of this OP1 minus 1 direction OP1 minus 1. So it's called resolved conifold because this is a resolution of conifold singularity. And this is, it might be well known, but as a resolved conifold is one of the most classic examples of 3-Calabi variety. And one reason why people are interested in Jacobi algebra is because it provides a non-commutative model of 3-Calabi varieties. And it's also the playground where DT theory happens. So let me define or explain what is Kuntz-Lewis-Sorbel and cohomological algebra. So given any smooth variety x with a function, then there's a construction of a vanishing of a perverse sheaf given by vanishing cycles, and this sheaf is supported on the critical locus of this function. So one can think that the purpose of this sheaf is to study the singular nature of this function. So the critical locus are exactly the points on which differential is 0. So this perverse sheaf measures how singular the function is. Now, given any quiver with potential, because potential is a cyclic element, if we have any representation, then we can always evaluate the representation of the cyclic element to get an endomorphism. And once you have an endomorphism, you can think that's kind of a matrix. And given a matrix like square matrix, and given such a matrix, you can take the trace. So you can define a trace map from this stack of representations of a quiver to C. And the crucial thing is that the critical locus of this function are exactly the representations of D-dimensional representations of Jacobi algebra. So this is exactly so if people are familiar with DT theory, this is the setting which things are locally in DT theory. That it's one thing that the categorization of DT invariants locally look like globally critical locus. And this is an example where you have a function over a variety which is over a stack which is smooth, and the critical locus is exactly the Jacobi algebra. Now, Kuntz-Lewis and Sorbel, they defined algebra structure on the critical cohomology of the stack MDQ. So by critical cohomology, I mean we take coefficients in vanishing cycles. So this vector space AQW is defined to be the direct sum of all dimension vectors, the cohomology of this stack of representation of quiver with coefficient in this perverse sheaf of vanishing cycle. And this is, I'm not familiar with physics, but supposed to give a mathematical definition of algebra of VP states. Now, how do they define this algebra structure? This is also defined by similar Hall algebra kind of product. So you take again the stack of short exact sequences, which is exactly the same. Just instead of taking the representations of preprojective algebra, we now just take the usual representations of the quiver. And again, you have the maps in which forget the first and third thing in the short exact sequence, or just remember the second thing. And so you get a map to MDQ times MEQ, or you get a map to MD plus CQ. Now this map is again code scheme, it's again proper because if fibers are code scheme, but this morphism is in fact like smooth in this case. And in fact, for any torus T which leaves the potential invariant, you can also consider the T equivalent homology, and what can we do? And then you can define a similar Hall algebra structure on the T equivalent homology of quiver with potential. So instead of taking this vector space, you can take T equivalent homology. So is this clear, the product structure? Is there any questions till now? So I define this new algebra come out of with any quiver with potential, and now explain why it's related to, or how it's related to our work with preprojective algebra. So the point is that there is a dimension reduction isomorphism. So which takes any this CoHA, equivalent CoHA, or so this T again here means that it is replaceable. Like we can forget, or like we can take any torus. So in particular, no torus also.
Yeah,
So-
Shivang, actually, it's not Davison. It's already in our paper of 2010. There is a dimensional reduction. It's much more general, of course, than just with a preprojective algebra. But yeah.
Yeah, sorry. So you mean the paper of you and Ren?
In the paper with Maximon on cohomological whole
okay.
algebra. Yeah, there is a version which is quite actually it's even more general than this. Yeah, but it's not Davison. Davison wrote PhD thesis, kind of filling many details which we sketch, but I think on this part we were quite clear.
Okay. Sorry.
Yeah. And actually, I considered this dimensional reduction in the way that, I mean, it's more, for me, it's more difficult to compute cohomology with coefficients in the vanishing cycle. So when you said that it's difficult to compute preprojective this cohomological whole algebra in preprojective case, for me, it was a simplification because you deal just with equivariant cohomologies of some spaces, which theoretically you can understand, but it's almost impossible to compute explicitly cohomology with coefficients in the sheaf of vanishing cycles. It's theoretical device. So then, yeah, okay. But the dimensional reduction, of course, it's in our paper. Yeah, you should look at it.
Okay. So yeah, I'm sorry. I will replace that. Yeah, I mean, but somehow like this is what I was trying to say, that the advantage here, so in the preprojective algebra, you say that you can just define it to be the equivalent cohomology of some space, which might be much easier to study. But the problem is that the space is not smooth, and for example, commuting variety is an example, which is extremely
Yeah, but when you compute cohomology coefficients in the sheaf of vanishing cycle, this sheaf is concentrated on the singular variety, on the critical locus. So then you still have something singular. But how to
that's true.
compute?
It's supported on the critical look. Yeah.
Yeah, I
But
mean, it's maybe it's a matter of taste, but if for you it's easy to compute cohomologies coefficients in the sheaf of vanishing cycles, that's great. I cannot compute it in a except of very simple examples. But anyway, okay. Sorry, go ahead.
yeah, for me, I think so. The reason why it becomes easier is because of the next statement. So if you take the Cohen-Shivang cohomological algebra with zero potential, then what we are looking at is the T-equivalent cohomology of some stack with constant with coefficients in Q. And this is just very easy to calculate in some sense because it's cohomology, because this stack is defined to be is defined by taking the quotient of the affine space, which is homotopic to a point. This is just E times DLD equivalent cohomology of a point, which is just this. It can be just identified to a polynomial ring, so symmetric polynomial ring. And the cohomological Hall algebra product can then be explicitly written in terms of product of the symmetric polynomial. So what is that when the potential is zero, then you can still consider CoHA, and then their product is a very explicitly one. You have certain polynomials, and then there's a multiplication rule given by shuffle kind of product. Now, to study quivers with potential, the technique generally which one aim for is to somehow get an embedding into an algebra where we can do product easily. And so the properties of vanishing cycle allows you to do that, for example. So you can have you can construct a natural map where you start with the T-equivalent cohomology of this type with coefficient and vanishing cycle, and you can define a map to T-equivalent cohomology of this type with coefficients in Q. And if you take the direct sum over all dimension vectors, then we get a morphism of graded algebras, which goes from T-equivalent cohomology of triple quiver with triple potential to T-equivalent cohomology of this morphism of graded algebras, which goes from T-equivalent cohomological algebra of triple quiver with triple potential to T-equivalent of triple quiver. So here the product is very explicitly known. Now, the one thing is that we define this map, but it is not clear if this will be an injection. In fact, for the case of when there is no torus, then this algebra, Q tilde, is in fact commutative. It's a super commutative algebra because of the way it is defined. One can check that this product, the shuffle product, is commutative. While this algebra on the left, even without the torus, is non-commutative. We don't have any torus, and this is not an injection. In fact, it can never be an injection. Almost never be injection. But then there is a theorem of Davison and independently for Davison, and so it was done by Schiffmann and Vasserot, and then later by Davison somehow improved it to show that there is an embedding. So when you take a torus action, which scales the arrow with some weight, the opposite arrows with other weight, and then loops with weight -1, then this map indeed becomes an injection. So basically, in this case, when you have this T-equivalent cohomology, T-equivalent injection, then point is to understand what is the image of this algebra. So, and then again, another interesting thing is that after localizing, so here I'm defining algebras which are over the cohomology ring of a point. Now, if we allow to localize them, so it's written in this statement that so if you take the usual cohomological algebra and you tensor it with the fractional. So this is the cohomology ring of a point, and this is the fractional field of the cohomology ring of a point. So you allow to invert the equivalent parameters. Then this algebra is this algebra is spherically generated in the sense that it's generated by the smallest possible dimension vectors. And so this is the thing which is, so the point is that when we study the spherical part of the algebra triple quiver, which can be explicitly written in terms of triple product, then what we get is the cohomological algebra for triple quiver, triple potential, but only after localizing. And this has been the work which has been done by Yang Zhao for AD and affine AD quivers, and also in Rapsec, Sovilman, Yang Zhao, they do it. They don't do the localizing, but they also consider the spherical part of the CoHA of triple Jordan quiver and triple potential. But in the case of cyclic quiver, if you don't localize, then these algebras are not spherically generated. As I said before, the fundamental class of the surface comes up, and that is something which is in dimension 1, 1, 1, 1, 1, and it is of negative cohomological degree. So what do we do? So we first study the non-equivalent case, and because it's known that the T-equivalent cohomological algebra is a flat deformation of the non-T-equivalent, like the usual cohomological algebra. So studying this provides enough information or set of generators for this algebra. So we first study what this is. So this has been done by so many structural results are known for the case of quiver with potential. So let me explain one foundational structural result in some sense. So if you take any symmetric quiver with potential, then there exists a filtration on the cohomological algebra, such that we have an isomorphism. You take the symmetric algebra in certain Lie algebra with tensor with U, then it's isomorphic to the associated algebra with respect to this filtration of the homological algebra. So you should think of this one can be interpreted in two ways. So first thing is that this kind of suggests that these algebras AQW are some sort of Yangians, in the sense that there exists a filtration such that they are exactly of the same size as the universal enveloping algebra because of the PW theorem. So another way to think of this is that this is because of this integrality, in the sense that in general for DT invariants, if one can define this vanishing cycle, there exists a categorification of DT invariants, and one expects that the cohomology with respect to that categorification is exactly the symmetric algebra in certain smaller thing called the BPS cohomology. And this is an instance of that. This is as a vector space, this is same as the AQW, and what you get is some primitive elements, which is a BPS cohomology tensor with some cohomology ring of C star. So let me say a few more words. So this Lie algebra BPS QW, it's a Lie algebra. It's some vector space which sits inside the cohomological algebra, and the Lie algebra structure is given by the natural commutator Lie bracket coming from associative algebra structure on the cohomological algebra AQW. And the CU, what does the CU mean? So the thing is that the way I define the stack of representation of quiver, you are parameterizing some representations. For every vertex I, you have a tautological bundle which is exactly records the vector space on that point. So in particular, when you take the determinant of this tautological bundle, you get a line bundle. So you get a map, the determinant map from this step to BC, to point mod C star. And you can take, and then if you take a pullback, then you get certain homology of the point mod C star is exactly CU to some element, to some endomorphism of the cohomology of MDCQ. And that's exactly the CU. Now, so if one wants to calculate what this AQW is, one needs to understand what this Lie algebra is and this Lie algebra tensor CU, and what this Lie algebra tensor CU is. And For triple quiver with potential, it's slightly easier to consider this. In fact, for conifold, for the case of conifold, which I explained before, this vector space is not, so when you have such an isomorphism, you can expect that this vector space might be closed under the commutative bracket, not just the VPSQW, but VPSQW tensor CU. But that is not true. But for the case of triple cubic potential, which is what we are doing right now, this vector space GVPS tensor CU is closed under Lie bracket. And that's the work of Davison and Kinjo. I don't think there's enough time to explain what they do, but point is that there is a Lie algebra structure on GVPS QW tensor CU also. So now we come back. Let's take our case, the case of cyclic quivers. So as I said before, so we have to consider the BPS Lie algebra, and then we have to consider BPS algebra tensor U, and we have to compute the relations between them. So an important theorem which allows us to say something about the BPS Lie algebra is its relation to Katz's polynomial. So the theorem is that for any quiver Q, there is a polynomial called the Katz's polynomial, which counts the absolutely indecomposable representation of Q over some finite field FQ. And the theorem of Davison is that the Poincare polynomial of the BPS Lie algebra is exactly the Katz's polynomial. So now if we calculate it for the case of cyclic quivers, then it automatically tells you that there are automatically gives some generating set of the cohomological algebra. In particular, it says that there are these terms, so U times R dot alpha delta I. So there is some element which is the same as what we were using before, something which is supported on dimension delta I. And there are some elements which are supported on the imaginary roots for every K. Now we have this generating set, but we don't know the relations between them. So to compute the relations, what we do is that we construct an action on equivalent Hilbert scheme, or which is an example of Nakajima quiver variety in this case. Or one can also consider the construct an action of a sub-half of this cohomological algebra on the cohomology of Hilbert scheme of points. Now there is already a known action of certain Lie algebra on the equivalent Hilbert scheme due to Nakajima, where they construct an action of a affine Lie algebra. So what we can do is that we identify some of these actions, some of these actions coming from CoHA with the action due to Nakajima in this case. Similarly, there is also another action of Nakajima on Hilbert scheme of points on surface, and these operators gamma k delta, they act like Nakajima operators on Hilbert scheme of surface. So this, along with some statements come from Land relation, from the work of Land, Manford Land, and geometric Mackey correspondence, allow us to compute the relations. So let me state the second theorem. So we consider WK tilde a Lie algebra with some generators spanned by TKA, where X is some matrix inside as some trace set matrix K plus K times K trace as matrix, and some elements TKA with some specific relations. Then the theorem is that for the cyclic quiver of length K plus 1, there is an isomorphism of algebras. Where you take the preprojective cohomological algebra of this, then it's exactly the universal enveloping algebra of this Lie algebra. And then there is a minimal generating set of the positive half of this Lie algebra, which one can compute also the image of those elements inside the T covariant case. And that's how I proved the theorem before, about the Yangians. And finally, this Lie algebra WK tilde is also not something like which is I mean, this is, so the way I define it is extremely random. So I can say a few, but like one can also see this in nature. In fact, in the work of Kaito, Repchak, Zhu, they define certain algebras, and this is exactly the central limit of this algebra. So let H be a formal variable, and let dH of C star be the algebra of H differential operators on C star. Then it's an associative linear algebra, which is generated by some variable z plus minus 1 d with some relations. Then you can take this algebra tensor with this with the algebra of matrices, and you can construct. So now it's an associative algebra. You can consider the Lie algebra structure on this associative algebra. So this is the algebra which is spanned by some elements z and dA x, where x is some matrix inside G and K plus 1. Now you can define another kind of integral form of this Lie algebra. So you take a subspace where you have these elements, the original generators, a tkax, where x is in GL, and you take the other generators, the small tk, you just divide them by 1 over h, and take the th linear subspace generated by these. Then the central limit of this is exactly the Lie algebra which we were considering before. And the final theorem is that we can also see this by cohomological algebra. So if we take the cyclic quiver and C star be a torus which acts on the original arrows with weight 1 and opposite arrows with weight -1, then there is an isomorphism of algebras. And that's what I wanted to say.
Okay. All right. So is it you? Okay. Okay. So this is the deformed theorem. All right. So are there any questions? Yeah. Okay. Yeah. Last part is quite interesting about this relation between preprojective algebra and differential operators, because preprojective it's somehow analog of the moduli, representative moduli of Higgs bundles. So deformed, it's something like differential operator. So then it's somehow you quantize a cotangent bundle to C star. Yeah. Okay. Yeah, it's interesting. Yeah, and you consider the action on the Hilbert scheme of this quotient C square modulo the cyclic group of order K. Yeah.
K plus 1.
K. Well, yeah, K plus 1. Yeah, you see in that paper you mentioned, like with Rabchak, Yang, and Zhao, we considered kind of three-dimensional story. It was an action of spherical part of covariant spherical part of CoHA on the moduli space of Nekrasov spiked instantons, and it's kind of three copies of, if you'd like, of Hilbert schemes for C square, but they interact in non-trivial way when two coordinate planes intersect along the line. I'm just wondering whether you can add three cyclic groups to that story and to get. I think people have not done it.
That might be possible. I mean, I know that So if for the ADHM quiver, if you can also have action of cyclic group, and the
Yeah,
fixed
of
point is
course.
exactly the chainsaw quiver variety. So
Yeah. That's true. That's actually what I got from your talk. Yeah, but
yeah.
if you have, you see C square, it's kind of simplest case of Calabi-Yau. I don't know what happened. I mean, Dylan Batson, he considered more general surfaces inside of toric 3 Calabi-Yau. It's more general theory, but for simplest one, if you have C star, like we had with Mira, Yaping, and Fang, you can add three cyclic groups of different order acting on each. I don't know what we recovered was a shifted Yangian, whatever.
Yeah.
No, just a fine Yangian, but for more general 3 Calabi-Yau, you can have shifted Yangian. There are many Yangians,
Yeah.
But if you add cyclic groups, yeah, it can be another
Yeah.
version. Yeah. Okay.
That would be interesting. Yeah.
Yeah. More questions?
Yes, I do.
Okay, then I leave you as a chair because I have to go. Sorry.
Yeah.
Because
Thank you.
yeah. Okay. So thanks for the talk. Yeah, very good one.
Okay, here I have so you are the D algebra you get here, you're using the notation W. So
Yeah.
do you have
I
anything that because the construction seems to be also very close to the W algebra.
yeah, I think so. I mean,
Do you have any indication because it's coming from the differential operators and with the original affine D algebra?
yeah, so for the case of Jordan quiver,
Uh-huh.
this algebra turned out to be exactly universal enveloping algebra of W1 plus infinity D algebra.
Okay.
And here we have W1 plus infinity tensored with matrices. So,
And
I mean, here
the
I call them W in the setting that they are some sort of W1 plus infinity algebra tensored with matrices.
uh-huh. So
Yeah.
you haven't looked at the possible connections with the W algebra.
So these are not the WKGLR
Okay.
W algebra. Yeah.
Yeah. Okay. So
That's why I'm sorry for.
but I'm sure it is related in some sense.
They are related. They are related for sure. I mean, so in fact, there is, I think, these algebras these Yangians which I constructed. There is another definition of them which goes by taking the limit as tends to infinity of some vertex algebras.
Yes, that's
And
what
I
I
think
was
there's a
thinking.
shadow of that story
Mhm.
after taking the center limit. Yeah.
Actually, that's a part of my interest because in the cohomological setting, and Joyce already has a vertex algebra structure on the
Yeah.
cohomological on the stack side, and whether this will be. But what I found interesting in the last results, the cohomological whole algebra for the preprojective algebra, and instead of closer being Yangian, but it's rather than, which is a universal enveloping algebra, or the algebra.
Yeah.
This time it's not over the field, but over the polynomial ring, right?
Yeah.
So the quantum side, especially the h, the parameter completely being split off, it becomes. But of
You mean
course,
the last term, right? Yeah.
H is involved in the definition of the W algebra. Yes.
Yeah.
H is in the structure of the W algebra.
H is in the structure of the W algebra. Yeah.
Yes.
Yeah.
So
But
that
I
was
agree, it's kind of surprising that there is a universal enveloping algebra. The reason why there is a
that's surprising to me.
So I didn't talk about that, like why it is a universal enveloping algebra, but
Uh-huh.
but basically there is a co-commutative coproduct. So what we do is that for triple quiver with triple potential,
Uh-huh.
exactly preprojective algebra with some endomorphism. We can look at the eigenvalues of this endomorphism to give
Okay.
CoHA some factorization algebra structure over A1. And in the case when you don't scale this,
I see. So here it's already that in the three-dimensional case, it's already the universal enveloping algebra of the affine BPS stub algebra, which
yeah,
is a graded algebra in the graded sense. Am I right?
in braided, in what sense? Sorry?
In the graded
Yeah, it's a
algebra.
graded algebra, yeah. But it's only in the setting when you consider triple quiver with triple potential. So it's not true for the case of conifold, for example. But for the case of triple quiver with triple potential, there is such a coproduct, which makes it a universal enveloping algebra.
Mhm.
Yeah.
Okay, well, that's interesting. I'll probably have more questions. I'll send the email to you.
Yeah, that would be very nice. Yeah. I can also send it in the relation between WK algebra. I know one reference where it is it's definitely related. Yeah. Okay. Thank you.
Thank you.